Before we jump into section 3.4, discussing the properties of logs, I just realized there was one quick idea I forgot to cover in the previous video from section 3.3, and that is finding the domain of our basic log functions. I also want to take a moment to point out that as I'm shifting to making more of these videos, my notes go right along with these videos, but it's still always a good example to continue reading through your book. Good examples, make sure you stick with the examples that really go through the same types of questions that we're going through in the notes. Sometimes our book gets a little carried away, has some extra, but again, still can make good use of it. Just make sure you're following the same types of examples that we do in these notes. But now, domain of our log functions. When I looked at our basic log graph, we talked about the domain was 0 to infinity, but not including 0 because we had the vertical asymptote there. So generically, for a plain log-based b of x function, the x, the argument inside the log, has to be greater than 0. This is our last trouble thing to consider when it comes to finding domain. We've already discussed having negatives underneath square roots, and we can't have that. We can't divide by 0, and we can't take a log of 0 or the log of a negative number, right? Think about that for a moment. If my base was 4, 4 to what power gives you negative 16? It can't happen. If 4 is already positive, it doesn't matter what exponent you raise it to. Positive, negative, whole number, fractional exponent, you'll never end up with a negative. So we can't have a negative inside a log function. So what we're going to do to find the domain, we're going to treat this very similar to how we found the domain of square roots. We identify a log as a trouble spot. We look in the inside of the log. Notice I don't care about this. The x cubed is fine. The minus 4 in front of the log is fine. It's all about what's inside the log. This is where trouble can come up. With the square root, we would look at what's underneath the square root and set it greater than or equal to 0. Well, in a log, we will take what's under the log and just make it greater than 0. No equals, just a plain greater than. And now we'll solve this inequality. This happens to be a simple one. I'll subtract 8 from both sides and then divide by negative 8. Not to forget, when dividing by negative, you still have to flip the sign. So we end up with x is less than 1. So the domain for this one, we want less than positive 1. So I would have negative infinity up to 1, not including. We do not have the equals here, so I would just get the parenthesis here. The second one, very, very similar. I didn't even put any extra pieces. I'm just focusing right on the log itself. What's inside the log has to be greater than 0. But when I set that up in this problem, this is tougher. This was a simple inequality, able to isolate x, just remembering multiplying or dividing by a negative is when we flip the sign. But in an inequality like this, go back, look at section 2.6. This is the type of inequality we were dealing with, a polynomial inequality, and it takes a little bit more than just this. But this one is not terrible. It's already in terms of 0. So I'll set it equal to 0. Factor to solve, nothing too crazy here, just a common factor of x. So x equals 0 and x equals 4 are my two important values. I'll put them on my number line, and I'll be doing my test intervals. I'll pick an x before 0, so negative 1, negative 1, negative 5, two negatives, make a positive. Now I'll go inside of here, and I'll use x as positive 1, 1 minus 4 is negative 3, so a positive negative, which is a negative. And now something bigger than 4, I'll use x as 5, positive 5, 5 minus 4 is positive, so positive, positive gives us a positive. I want these two intervals because the whole idea for the domain was where is this greater than 0, so we want the positives, and the domain for f would be this interval and this interval, so the domain of f would be negative infinity up to, not including 0, and then starting just past 4 and going to positive infinity. So a good problem, just to realize that in everything we do, there can be potential overlap. Both of these problems are focusing on domain. This happened to be an easier one, easier to solve. This one was a little more complicated, so we had to use a little bit more of a technique. But again, just seeing how these ideas can overlap. We needed this to be greater than 0, and just in order to solve that inequality, happen to need a little more technique here than we did here. Okay, so now we can get back into the rest of our properties of logarithms. And all these still come as the inverses for exponentials. So we have all these properties for exponentials. We have things like b to the x times b to the y is b to the x plus y property. Well, this property number 1 is the inverse of that. Notice what I just said. So if I had b to the x times b to the y, that would be equal to b to the x plus y power. If we had multiplication of exponents, we ended up adding those exponents. Look how everything flips in this property. If I have multiplication inside of a logarithm, this becomes 2 separate logarithms, but still attached by addition. So I'm not going to formally prove why this is the inverse of this. I'm just trying to point out why these are related. Now back to these 3 properties. Our book does these one at a time. They formally call this the product rule because you have a product inside your log, the quotient rule, the power rule. I don't like to use those names. For those of you who move into calculus next semester, you will hear those with respect to derivatives, so I don't like to create confusion. We shouldn't use the same name for 2 different things. So I just prefer to call these the expansion and contraction properties. Our book again goes very slow through each one, shows how you could expand if you have something like this going from the left side to the right side, and vice versa. If you want to contract, you'd be starting on the right side and going to the left. But I want us to see all these together and get used to using these all together. We'll do some problems where we're expanding, so we'll keep working from the left side to the right, and then we'll do some problems where we're contracting, so we'll go vice versa. We'll kind of start from the right side and go to the left. But let's explain these for a quick moment. What we have here is the log. Doesn't matter the base. Notice I just used generic b for all of these. But whatever base we have on this side, we have the same base over here, and vice versa. If we want to contract, we need them to have the same base to contract and still have that same base in its log. But the idea, if I have stuff attached by multiplication inside the log, that I could separate them into 2 separate logs, each piece going in its own logarithm. Well, the parallels of math. If where multiplication leads to addition of 2 separate logs, well then division will lead to subtraction of these 2 separate logarithms. Here the order makes a little bit more of a difference. If you goofed and put these in the opposite order, well, log A plus log B or log B plus log A, same thing. But when you subtract, make sure it's the log of the top value minus the log of the bottom value. Just go back to number 1 for one more moment. This looks like it can only be used for 2 things if it's A times B. But if it was A times B times C, we would just get 3 logarithms separated by addition. It's not limited to just 2. We would just keep going. Formally, we could use the property twice. We'd have AB times C and get log AB plus log of C, but then we could keep expanding. So just to realize right off the bat, as many things are attached by multiplication, we'll just keep expanding by addition. And that's really what happens in number 3. Number 3 is really just a repeated use of this. A to the n power is A times itself n times. So you would keep getting log A plus log A plus log A plus log A, and you would have like terms. How many of those? You'd have n of them. If this was log of A cubed, that would be A times A times A. So log A plus log A plus log A would give me 3 log A's. So that's the understanding, but that's the understanding of why it works the way it does. But just to see the quick shortcut, if you've got that exponent pops out in front as a multiplier. So let's start with a few. Let's fully expand the following logarithms. And let's look at number 1. Let's start off with log base 2 of x to the 4th y cubed. And all we need to realize here is that I can't jump and start with property number 3. Realize one thing, everybody, the numbers on these properties don't matter. You have to understand the properties themselves. We won't be proving and say by property 3 or by property 2. So it's just important to know the results, not the number. But just since we have this up, realize I'm not going to start with this one. This only works if the exponent is on everything. So I have exponents here. I have exponent on x and on y, but I have nothing on both of them. So I'm actually going to start with property number 1. I've got x to the 4th times y cubed, so I'll get log base 2 of x to the 4th plus log base 2 of y cubed. And so far, good work so far, but we're not done. Fully expand the following logarithms. Can we keep going? This is a little bit like factoring. A lot of factoring problems are done in one step, but many of them take a couple of steps. So that's what we're seeing here. We did some initial expansion, but now that we've done that initial expansion, now we get to use this third property in both of these. Because now that exponent is on everything that's inside. Same thing here. So this 4 out in front is a multiplier, 4 log base 2 of x. Same thing, 3 out in front, 3 log base 2 of y. Some people always like to keep their parentheses around what's inside the logarithm, but when all that's left is one simple term, there's no need for parentheses, so you could leave it like this, but a lot of people do like to keep the parentheses for good habits, for when you absolutely need them. But that's it. That's the end of problem number 1. We fully expanded. Number 2, let's look at log of the square root of 3x minus 4 over the quantity x cubed minus 2 to the 5th power. Again, a lot going on here, but the first big picture item is that I've got these two bigger, uglier expressions, but they are attached by division. So now I'm going to start with the second property. I'm going to take log of the top one minus log of the bottom. Every once in a while, when it comes to the expanding, the book likes to leave one that you could factor, and then through factoring you could keep expanding. I don't want to go down that road. I just want you to get used to the properties, not also trying to consider too much extra. But now, similar to the first one, we've got the division separated. Now we've got ugly pieces, but now each of these pieces have exponents. This one is more obvious. The 5 is on everything, so that 5 can go out in front, minus 5 log x cubed minus 2. And that's as far as this one can go. You can't expand this any further. A lot of people have a temptation, oh, let me bring the 3 out in front. But you can't do that because the 3 is only on the x. It's not on everything that is inside. And the second thing that starts happening, now people start making up their own expansion rules. This is literally as far as it can go, but people are so obsessed with trying to get that exponent out in front that they start making up rules, like log of x cubed minus log of 2. There is no rule like that back at the top of the page. That is garbage. That does not work. So that's as far as this one can go. Come back to this one for a moment. It's tempted to think that we're done, but now we have to remember radicals are exponents. The square root of 3x minus 4 is 3x minus 4 to the 1/2 power. So that 1/2 out in front, that was the exponent. It was on everything, so out in front, the 3x minus 4 left behind. And this is what I was just mentioning earlier. Both of these need the parentheses. If you don't have the parentheses here, someone would think the 3x goes with the log and the minus 4 is floating by itself. The x cubed goes with the log and the minus 2 floats by itself. But those are the arguments inside your log functions. And this one happened to be the common log, log base 10, but that didn't matter. As far as the expanding was concerned, didn't matter. Just at the end that these were all common logs as well. Okay, let's do one more, and then we'll do some contraction problems. So number 3, let's look at log base 5 of x cubed 5x minus 1 squared, all divided by x squared plus 1 times x cubed plus 4 to the 4th power. This is big, looks ugly, looks messy, but all we need to realize, and once we get a little better, for some of you, you're literally just learning this, but as we get a little bit better at using these, some people start to get a little faster. Some people, once they get a little practice, they go back here and do this in one step, do this in one step. They're thinking about this step, but they move right into the second step, cleaning up the exponents that were available to move after we did the initial expansion. And some people start to realize things like, hey, everything that's attached by multiplication in the numerator will get a plus, and everything that's attached by multiplication in the denominator will get a minus. So I'm going to do this one a little slowly first, then I'll come back and show you a little bit of a faster version. If we're going to do this one step at a time, the first thing I have to do is look at all of this divided by all of this is the big picture. And I would do that expansion first. Log of x cubed 5x minus 1 squared minus, log base 5, don't forget the base, minus log base 5 of the x squared plus 1 and x cubed plus 4 to the 4th power. I took care of the big picture division, and now I get both of these have issues with multiplication. So now I would get log base 5 x cubed plus log base 5 5x minus 1 squared. I've used the multiplication expansion right here, and I'll do that same thing here. But here's the tricky part, everyone. That negative is out in front of this whole log. So that negative will be out in front even after I expand log base 5 of x squared plus 1 plus log base 5 x cubed plus 4 to the 4th. If I distribute that negative, leave this is done. I mean, I still have exponents I'll clean up, but just so far that's okay. Log base 5 x cubed plus log base 5 5x minus 1 squared. But now right here, distribute that negative minus log base 5 x squared plus 1 minus log base 5 x cubed plus 4 to the 4th power. I have no problem at all if you need to do those two steps to get here. And that's not a bad thing, especially if this is the first time you're seeing this type of an exercise with logarithms and using these properties. But look back to the beginning and realize how nice it would be if we could just jump to this line. Everything on top gets a plus in front of the logarithm. Every piece in the bottom gets a minus in front of its logarithm. That could definitely save some time. And some people start to realize this is not perfect, but for a lot of these problems, use the multiplication and division expansions first, and then clean up with any exponents left behind. So right here, that exponent is on everything, 3 log base 5 of x. That 2 is on everything here, so plus 2 log base 5 of 5x minus 1. Can't do anything more with this one. Yeah, there's an exponent, but it's inside the argument. It's not outside on everything, so that one is as good as it gets. And then here, exponent out in front. Not this exponent, just this one. This is the one that's on everything. So minus 4 log base 5 x cubed plus 4. It's big, it's ugly, it's messy, but these properties can really help in a lot of different arithmetic computational situations. So right now, just getting used to a little practice using them. As we move to the next page and we start talking about contraction, we'll just realize it's basically the opposite. We'll start off with expressions like this, or like this, or like this, and we'll basically do them in the opposite way. In these problems, we saw expanding multiplication division tends to happen first, and the exponents is last. So when we contract, we do it the opposite order. We'd start bringing exponents back inside so that we have plain logarithms, and then addition puts them together as multiplication. Bring these exponents inside, and then subtraction becomes division inside the logarithm. Bring these exponents, no exponent here, bring these exponents inside. Then all the pluses go into the top, and then all the minuses go into the bottom. So let's try that. Contract the following into a single logarithm. Let's look at problem number 1. Let's do 4 ln x minus 6 ln y. Now I'm using natural log, but doesn't matter. So they're all natural logs. I can't start with the subtraction. The rule, in order to contract, I can't have a number in front of the logs. I need them to be plain log minus plain log. But here I've got 4 log and 6 log. So like we were mentioning a moment ago, we have to start by bringing these inside. Log of x to the 4th power minus log of y to the 6th power. And now I've got log minus log. So now, not 2 logs. It's not log of x to the 4th divided by log of x to the 6th. It's 1 log with the x to the 4th and the y to the 6th. Inside, attached by division. Let's do another, number 2. Let's look at 7 log base 12 of x plus log base 12 of x squared plus 5 minus 3 log base 12 of 7x minus 2. Well, now we have 3 pieces in our logarithm. Doesn't matter. This one is a nice simple log, but these 2 are not. So let's start with these 2. Bring that inside. Log base 12, x to the 7th power. This one's fine. Leave it alone. Minus this 3 inside. Can't apply to both. Has to be applied to everything. And remember, what I'm saying here, it's not 7x cubed minus 2 cubed. That's not how. You'd actually have to FOIL it out. 7x minus 2 times 7x minus 2 times 7x minus 2. But we don't want to multiply it out. We just want to leave the exponent on everything. And now, you can go slow. These 2 are attached by plus. These get multiplied together. And then a separate step, then all of this would be connected to this by subtraction, so it would become division. But it would be so nice to do that all at once. The pluses are multiplied in the top, the minuses in the bottom. Well, there's only 1 minus, so there's only 1 piece in the bottom. Log base 12, x to the 7 times x squared plus 5, all divided by 7x minus 2 cubed. No reason, just like we said here, there's no good reason to FOIL this out. There's no good reason to distribute this. There's nothing wrong with that as an answer. Okay, so got a few problems. Some expansion, some contract. But now let's finish up and realize that these properties are also necessary sometimes to simplify. In those properties in the previous section, we talked about simplifying something like 5 to the log base 5 of x squared minus 7. And that as long as these come consecutive, an exponent and a log in its exponent with the exact same base, that these cancel, and we get x squared minus 7. And in this one, to realize those parentheses aren't doing anything at all. So we just get the x squared minus 7. But it has to be that perfect. So number 2, what if it wasn't quite that perfect? What if I had 5 to the 3 log base 5 of 2x plus 1? It almost looks the same as the previous. It feels like I should be able to cross these off, but I can't do it yet. Before I can cross these off, I need that 3 to be out of the way. They need to be consecutive. So my way to get the 3 out of the way is to contract. 5, the log base 5, 2x plus 1. That 3 went inside as an exponent, and now we get that perfect situation. These cancel. So now we get 2x plus 1 cubed. Similar, number 3. Let's do one more like that. Let's look at 7 to the log base 7 of x plus log base 7 3x plus 5. I see these 7 log 7s, but I can't cancel both of them. I can only cancel one, and it's got to be consecutive. So I can't cancel one piece and just leave this floating. What I need to do, combine these. Make this one logarithm. Again, do some of that contraction we just did. 7, that's just being left alone. These can contract to log base 7 of x times 3x plus 5. And now these can cancel, and we would finish with the x times 3x plus 5. Last thing we're going to do for today. Oh, I should have pointed out, I'll do one more here, number 4. If I have something like log base 5 of 5 to the 2x minus 1 power, we've seen from that cancellation idea that this is another perfect. Now I'm starting with the log first. There's nothing special about 5. I just picked it for a few of these. But I've got the log base 5 and the 5 is an exponential, so that these would cancel and we'd be left with 2x minus 1. That comes from a direct property we had in our previous lesson. But we could also use these expansion properties. The 2x minus 1 is the exponent, so the 2x minus 1 could go out in front as a multiplier, and then I'd have log base 5 of 5, and 5 to what power gives you 5? That would be 1, so we get 2x minus 1 times 1, the matching 2x minus 1. So just pointing out, now that we've got these rules, that allows us to go back and reconsider some of our earlier problems and realize why some of them worked out and simplified the way that they did. The last thing for today, for this topic, is to see that we can always change the base. This really comes up a lot with computation. What good reason would we have to change a base? Well, most of the time, the reason would be we want to use our calculators. We've mentioned we only have natural log and common log buttons, but we've seen how we could handle other problems. So I'll demonstrate how to use this in just a moment, but let's see it in the context of a problem. Let's evaluate log base 5 of 125. Well, if we remember our basics of logarithms, we would think of that as 5 to what power equals 125. Do a little arithmetic, think about it. Well, 5 to the first is 5, 5 squared is 25. Oh, 5 cubed equals 125. So the answer is 3. But, and I really hope, everybody, we need this understanding. This idea of inverse is the main key to understanding logarithms. But realize, just because this button is not on your calculator, we can still check this answer. But the way to check is the change of base. We need to change it to a base that's on our calculator. So we've got either common log, base 10, or natural log, base e. But either way, it works out the same. If I wanted to make this common log, log base 5 of 125, look what happens here. The old base goes down here inside the logarithm, and the new base comes up in both new logarithms. So this literally, the log old base of whatever's inside equals the log of the new base of whatever was inside divided by the log of the new base divided by the old base. It's a little ugly to say, but when we write it out, we'll see it's not that bad. So if I want to use base 10, common log, this would be common log of 125 divided by common log of 5. The alternative, I mean, again, I could change this to any base. I could change this log base 7 of 125 divided by log base 7 of 5, but that doesn't help. At least by putting it in this form, now I can go back to the calculator, log 125, just make sure you close your parenthesis, divided by log 5. Very big difference in our expansion formulas. Our expansion, we had division, became separate logs attached by subtraction, or contracted into one log with this division on the inside. That's a different situation than what we have here. These are two separate logarithms. And notice when I hit enter, there it is. Plain old 3. And nothing special about common log. I could have done the same thing with natural log, and it would have gone the same way. Natural log of the original inside divided by natural log of the original base, and the same thing would happen computationally. Natural log 125, close parenthesis, divided by natural log 5, and there's your answer. This is especially helpful for some people who still struggle a little bit with radicals. That if they want to know something like, what is log base 81 of 9? 81 to what power equals 9? The square root of 81 equals 9. So it's 81 to the 1/2 power. That's truly what we should get. But again, it's not easy. Not everybody is so quick to make those radicals. They're not always perfect square roots. It can get a little messier as well. So especially when the problems get a little harder, whether it's because there's fractional exponents involved or if there are negative exponents, the calculator is a nice way to double check. So if I did that one here, I would do log of 9 divided by log of 81.5, which I could convert to a fraction. You don't need to. 0.5 is fine, but that is the same thing as 1/2.